So what is the Z switch here? I forgot to record, so I just turned the recorder on. So this is Y. Somebody playing with the switch for the third switch for Z, and we have W there. And again, you playing with that, so you can, since you're in charge, you can do whatever you want to do with it. You're flickering with that switch inside that box there. Oh. Then you make it go back here. I should have just deleted one of those gates there, just to make my life easy. And let's say 0 after that. What do you want W to be? You know what? I'll put it there. I was about to kill it, get rid of it, because I'm running out of space, I can tell quickly. So I'll make it small here. W was 0 for a while, till we reach this point. It went to 1, stayed 1 up to this point, and back to 0. So we have the switches on the boxes, and people just playing with them. 4 people, one is going up and down as when they feel like it, each one of you. So, and just X, Y, W, X, Y, Z happen to be attached to that circuit the way you see it up there. I want to show you actually what will happen to that circuit. Let's look at X and Y. That's the top one, the AND gate. The AND gate looks at X and Y. You see 0 and 0. So what's the result? What is 0 and 0?
0.
So we'll stay 0 till this time. Then this one goes to 1 and 1. Oh, wait a minute, this is 0 and 1, right? This is 0, this is 1. What's 0 and 0? 0 and 1? 0. It will stay there till we hit this point. This is 1 and this is 1. What's 1 and 1? 1. So the gate will have to go to 1. And fortunately, it never really goes to 1 quickly. It goes like this, slowly to 1. And it will stay 1 till we reach this point. And what happens after that? This is 1 and this is 0. What will happen? This actually will go down to 0. Slowly, it will go like this. And it will stay 0 till we hit this time. Then it wants to go back to 1, and it takes a while to go to 1. And it will stay 1 till this time. Then what happens after that? It goes to 0. And 0, 0, 0, stay 0 the whole time after that. Well, if we are designing this circuit, there is a delay for us right there. To go from 0 to 1, we have a delay. Can you see it? It takes the function a few microsecond, millisecond to go to 0, 1. So you can't really read the value there. You got to wait for it till it reaches that value. It doesn't go 0 to 1 immediately. We like it to go 0 to 1, but it's not going to happen. Now, we're going to take this signal and we're going to OR it with what? With Z. So here's Z, and there's this signal. 0 to 1. Well, I see 0 or 0, so that's what? Z plus XY. Let's see what's going to happen here. 0, XY is right there, Z is right here. Just keep an eye on them. All the way to here. 0 or 0, 0. Then it's going to go to 1, right? Because that's 1 and 0, but it's going to be delayed now. So I'm going to push the 0 a bit longer. It's not going to happen there. It's going to go a little bit later. That's that delay there again. Notice it doesn't happen at the same time. 0 and 1 is 0. 0, 1 is 1, stays 1, stays 1, stays 1, all the way to here. When this one goes to 0, see that goes to 0? So it's going to stay 1 all the way there. But what's going to happen here now, this is what? 0, and this is 1. This is going to delay it actually to go down to a 0, but not by that delay, by 2 more of these delays. Because that takes a while for this. This is really treated as like this, the signal. It's 0 here, and it stays 1 here. That's how we look at it. That delay like this. So that delay, it's actually 1 up there, but it's 0 down here. So now it still sees 0 and 1, which is a 1, stays 1. And now it goes to 0, but it's going to be another delay before it drops to 0. So you get a delay from here plus another delay from here. 2 delays. So now you got to wait a little bit longer for this to see it. And you continue your pattern there. This is 0 right here till it goes to 1, and here stays 1 till it drops to 0. They're programmed to work that way. So let's continue here. This is 0, 0, 0. Then it hits the 1. It doesn't happen there till right there. Then it goes to 1 because of that delay there. So this one goes to 1. I get another delay, and it stays 1. This or this, let's add them. 1, 1, 1, 1, all the way to here, because that's when they both drop to 0.
So we're on Z, not W.
Oh, Z, where's Z? Right there. The one after it. So that one. And it's going to drop to 1. Again, there's that delay there, so it'll stay 1, and it will drop down to a 0. So you can see we have a problem with these gates. And again, there's 2 delays here. Notice we got a delay from before, delay from after, 2 delays. And the third one, I could have 3 delays. So when you see a circuit like this one, you go, this is nice. That delta means delay. There's a delay. There's a second delay to go through that. There's a third delay. The output of this goes into this. That's the 4th delay. The output of this goes into that. That's the 5th delay. The output of this goes into this. That's 6 delays. Even if it's microsecond, you already have 6 microsecond delays. There's not much you can do. Nothing you and I can do to fix that one. Unless we can come up with better equipment. Now, these delays used to be in the milliseconds a few years back. Now in the microseconds. The gates are nicer and faster. We do not have 0 delays. Nobody has them. Ideally, we like it to go 0 to 1. We can't. We can make it move faster in the micro and nanosecond. That's it. So that's not the best approach to do it. Plus, connecting these devices together. So now we have some chips on the market, larger circuits already built that we can use. That means I don't have to simplify my expression. I don't have to do the K-map. I don't have to do Boolean algebra. Just connect it and let it work. So what are these devices? Let's look at some of them. If you were building something, you want to test something in the lab, something simple, you can go ahead and build it. But if you're building something big, I can buy a decoder with a Xor Gates with another chip and do all the stuff without doing any K-map and simplifying anything. I don't have to simplify. I don't need to simplify. Or I can buy a multiplexer, color them, and I don't care what the expression looks like. Just plug it in, go this one, that one. It's done. So let's look at some of these. One of the ones we're going to be looking at, go back and revisit, is the 4-bit full adder. I don't know if you remember the 4-bit full adder from before. when you are adding 4 bits, and let's take some 4 bits and add them. Let's see when I add these two. For the first bit on the right side, is there a carry to start with? No. What's 1 and 1? 0. That's your sum. But now we have a carry, right? And what do you do with the carry? You put it right there. 1, 0, 1. That's what? 2. That's 0. Carry 1. 1, 1, 1. That's 3. That's 1. Carry 1. 1, 1, 0. Carry 1. So let's look at that full adder and see what it looks like, the inside of it. The inside of it will look something like this. I was crooked there, I guess. I have paper, grid, still crooked. Try to make it a little bit nice and neat. Okay, let's go like this. Each one of these, it's 1 bit, adds 1 bit for you. Each one of these. So going to this, we're going to be adding, if we call the top values here, if we call these like these are the A values, A1, A2, A3, A4, and this is the second number, B1, B2, B3, B4. So this one is going to have A1 and B1 going to it. The first digit from here with the first digit from here. It has a sum, will give me S1. It has a carry, we'll call it C1. So what's going to happen to that carry? That carry is going to be looped around and entered the second one. So that becomes the carry of this one, and this is the second digit, A2, B2. This is sum 2, carry 2. Again, we take that one, feed it back to this. And now we have the third bit, A3, B3. And we have sum 3. And we have a carry now coming out of it. That's the third carry. That carry now will be added to this. This is S4, sum of digit 4, and that's carry 4 coming out of the fourth one. A4, B4. When you buy these, that's a 4-bit adder will look like this. This is not attached to 0, the first one. You have to attach it to 0. Why? Because a lot of times you want to build what? An 8-bit adder. If you make this always attached to 0, you can't make an 8-bit adder. So if you want to do a 4-bit adder, you take another strip, one of these, put it at the end, and you attach this one to what? To that piece. And the carry from this will go to the fifth one now. That's why that's not attached to the ground. So your job, if that's your first one, to attach it to the ground. Now you have a 4-bit adder. You want to make an 8-bit, you buy another one, and you take this, attach it to that one. So from now on, when I draw a picture of a 4-bit adder, I'm not going to draw this diagram here. That's too much drawing there. So what I'm going to do is I'm going to make it look like this. A little bit bigger. And I'll explain how we use that to do addition and subtractions in a second. So this is a 4-bit adder when you buy them. We have 4 coming out, S1, S2, S3, S4. You have 4 digits for A and 4 digits for B. And you have a carry coming in. So this is A1, A2, A3, A4, B1, B2, B3, B4. And there's a carry coming out of this C out. So you want to make a 4-bit adder, you take this one, attach it to the ground. That's what my 4-bit adder will look like from now on. There's obviously a couple of pins you have to turn on and off, chip enable. Remember all the gates we did in the lab? We had 2 things to turn on. Pin number 7 was going where? To ground. Pin number 14 was going where? 5 volts. Without them, that chip wasn't on. All the op amps, no, we didn't do op amps, did OR gates and gates. If you don't turn them on, that's your chip enable to turn on and off. These will have the same thing. If I want to make an 8-bit adder, I buy another one of these, a 4-bit. I'll take this. I don't know why I made it longer. And I will take the carry from this now and do what with it? Move it up and have it feed to the next one. That's another 4-bit adder. And you have 4 inputs again. Another 4 inputs, A and B. 4 outputs, S1, S2, S3, S4, and you have a carry out. Now you have an 8-bit adder. You want to do a 12? You get another one of these, attach this to that one, and repeat the process. You want to have a 16-bit, you get 4 of them. When we start talking about adding and subtracting binary, I say, you know what, we're going to use the same device to add and subtract. Remember when we had subtractions, what did we do? Anyone remember? We did first the 1's complement, flip all the 1's to 0's, then we add 1 to it to get the 2's complement. Well, watch what's going to happen. We're going to use the same device to add and subtract. So I'm going to show you a 4-bit adder that's going to add and subtract for me. Here's my device. I'll put it in the middle because I need some space there. That's my 4-bit adder. Let's say I want to add A and B, or I want to do A minus B. So this is the A's. A1, A2, A3, A4. These are the B's, B1, B2. You write them on the side. And this is my carry. But instead of attaching this to 0 or 1, I'm going to bring it right here. That's my carry in. And this is going to be attached to this. I'm going to make it, for addition, I'll make it 0. For subtraction, I'll make that a 1. For addition, A for addition, I'll make it 0. For subtraction, I'll make it a 1. What I'm going to do actually beside that, that's not the only thing I'm doing. What I'm going to do is I'm going to take this and feed it to an exclusive OR. And that exclusive OR is going to go to B1. Now, in case you forgot, the Xor gate has 2 inputs here. This is also B1. How does this gate work? If both inputs the same, it gives you a value of 0. So if you have 0 and 0, you get a 0. If you get 1 and 1, you get a 1. But if they're different, you get a 1. 0 and 1, you get a 1. So when one of them is 0, one of them is 1, you get a 1. When they're both the same, you get a 0. And I'll do the same thing for B2 and B3 and B4.
If they're both 1, you also get a 0?
Yep. That's another XOR. And to this we have attached B2. Where's B2? How far? Right there. And that's B2 attached to that. And I get B2 here. And I get another one here, B3. And that's going to B3. Where's B3? Down here. And the last one is B4. So let's see what happens. When you make that pen 0, that's for addition, 0. You get a 0 coming in. There's no carry. That's good. But now you get a 0, a 0, a 0, a 0. What is 0 XOR B1? Well, the value of this will depend on B1. If this is 0, what's 0 or 0? You get a 0, the same as B1. If this is 1, what's 0 or 1? 1. So basically, when you put a 0 here, this will be B1. When you put a 0 here, this will be B2, B3, B4, you're just adding them, and there's no carry. Basic, straightforward. Oh, now what happens when you put a 1? That's we have subtractions. Now I'm supposed to do what? The complement. So if you put a 1 here, you have a 1 here, you got a 1 here, you got a 1 here, you got a 1 here. Let's assume B1 actually has a value of 0. What's 1 and 0? What do you get? 1. That's the opposite. That's the complement, isn't it? If B1 has a value of 1, what's 1 and 1? You get a complement. So once you put a value of 1, this will be the 1's complement. That will be B1 not, B2 not, B3 not, B4 not. You complement all the 1's and 0's. Then you're supposed to do what? Add 1. Well, if you have a 1 here, what's going to happen to that carry? You're going to add 1 to the answer. That does the 2's complement.
Beautiful.
Do you see it? This one does the one's complement. This one adds the one when S is 1. You have the 2's complement. Now go ahead and add them. So in place of having an addition or an adder and subtractor, we can actually do it with one chip that will add and subtract as long as you add these 4 exclusive OR to it. When you put a value of 0 here, these values will be B1, B2, B3, B4, straight addition. When you put a 1 here, this will be B1 not, B2 not, B3 not, B4 not, and this will add the 1 to it. That's the 1's complement, and this is adding the 1 to get the 2's complement, and now we can subtract them by doing addition, doing the 2's complement. So now that's a 4-bit adder / subtractor. By using the 4-bit adder and a little manipulation with that circuit. What else we have there? Well, we got decoders. We got multiplexers. We got encoders. We have PLAs, PAL, programmable logic array, programmable array logic, ROMs we can use. Can't cover them all today. On Thursday, we'll talk about decoders and maybe multiplex. On Thursday, we have a test. So